So on number 2, what did we get? You said 62.63? Absolutely correct, yes. So one thing I want to point out before I write that down on my screen, because I'm going to bump it up a little bit higher. I wanted to talk for just a moment, because we ran out of time yesterday. This piece right up on top, so the same thing that I see right up here, we call that hat. So in this first one, it would be y hat. In the second equation that I wrote, it's distance hat. It gets that hat over the top of it because it means the predicted value. And there is a substantial difference when we're talking statistics between an actual observed value, what we collected from our sample, and what our model would tell us we would expect, or what we would predict based on our model. So I'm going to come over here. I'll put that up on the screen as well. So again, that hat means our predicted y value. All right, tell me how you got 62.63 for part 2.
I just substituted number 5 into where x is and it says rubber bands.
Yep, absolutely correct. If we want to predict the distance, we have 25.33 as our starting point, as our y-intercept, plus 7.46, and then we're going to substitute in 5 rubber bands. And we get 65.63. Should we include units with that? Yes. What would our units be here? Centimeters. Yep. Does anybody have any question about number 2? So the group member later found the measurement for 5 rubber bands. They actually went and they tested it out. And they found that 5 rubber bands got 64 centimeters. How far off was our predicted value from the actual recorded value? How far off was our predicted value from number 2? How far was that prediction from the actual value when they went back and tested? What was our prediction again? 65.63. And when they tested it, they found out that it was actually 64. How far off was that prediction? Oh, thank you. I wrote the wrong number down. I'm so sorry. I had the 5 rubber bands stuck in my head, and so I wrote a number 5. I'm so sorry. 62.63. How far off is that prediction from the actual observed value of 64 centimeters? 1.37. Was our prediction too high or too low? Too low. So 1.37 centimeters too low. Thank you, ma'am. And then there's your third place. You're welcome. How did you come up with the 1.37 centimeters? Subtracted. So this is something called a residual. Residual is going to be the difference between what our model would predict for us and our actual observed value. And to find a residual, We take the actual observation and we subtract the prediction. So an easy way to remember which one comes first, because with subtraction, order really matters. What class is this again? AP Stats. A, P. A minus P. AP for our residual. So we're going to do the actual minus the predicted here. And then I want to be able to write this out as a sentence. Think about if you were writing, oh, our predicted value was this, and this is what we actually found. So I would write this out in sentence form by saying that our prediction, or our predicted value, was 1.37 centimeters too low. One of the things we never want to use as we're writing out explanations in sentence form, it is a very nasty word, because it is not specific. And so we want to make sure all along the way that there's no way our reader could get confused about what we're meaning. So we're going to write it out long ways. I want you guys now to predict the distance that Barbie would travel if the group were to use 20 rubber bands. Find the predicted distance that Barbie would travel if we used 20 rubber bands. You said 174.53? All right, because I messed up writing it down last time, can you guys double check that I actually wrote the number correctly? Okay. 174.53 centimeters. Would you guys trust that prediction more or less than our predicted value in number 2? Or about the same? Do you think it's going to be about the same off? What do you guys think? Yes, sir.
I would trust it more because it's based off the, what's it called? The regression line?
It's based off of the regression. Remember, our whole regression equation, what this exists for is so that we can try to make accurate predictions about what's going to happen if we do something that we might not have an observation for. So we had observations for 0 rubber bands, 1, 2, 3, 4 rubber bands, right? They forgot 5, and then they tested 6 and 7. How well does this 62.63 match up with the rest of the data that we actually had? Does it seem to fit in line with the rest of these values? Yeah, like 55 on one side, 69 on the other. I would expect something right around 60, 62, 63. That all makes sense. Do we have any number of rubber bands that are close to 20 that we could say, oh, this is probably reasonable. It seems to fit. We don't have values on either sides. This is something called extrapolation. We have to be really careful with extrapolation. When we use our model to make a prediction that is really far out from all the rest of our collected data, we're saying that we think our model is super accurate. We already saw that there was a difference between the actual and the prediction. Not a ton, 1.37 centimeters, that's, what about like this, right? Not a whole lot. But if I start getting further and further and further away from my data, if every single value from my prediction is off by 1.5 centimeters, as I get out to 20 centimeters, that's going to compound that error. and it's not going to be as accurate as when I'm working within this smaller data set here. So we want to be careful about extrapolation. What we did up above with the 5 rubber bands, where it was in the middle of data that we had actually collected, that's called interpolation. And that's usually going to be reasonably accurate. Extrapolation is going to compound any kind of errors we see, and it can be very far off. We should trust this less. We're going to trust it less because it's far away from our collected data. And extrapolation can work both ways. If I have a very, very, very small value that's far away from the rest of my collected data, or a large value in this case with the 20 rubber bands. I'm not saying that we would never use this for predictions, but I'm not going to bet my life on it. I wouldn't make an actual bet based on extrapolation. Interpolation, I might lay money on that. I'm pretty confident that that would be reasonably accurate. Does that make sense? Okay. Let's go look at question number 5. See if I can grab this guy here. What is the y-intercept of our regression equation? 25.33. And that would be in centimeters. What does it mean? Yes. So we want to write this out in sentence form. Whenever they ask us, like, what does it mean or explain, we want to make sure that we're writing this out in sentence form. So I would say very specifically, is that the observed value with 0 rubber bands? What did the table say for 0 rubber bands? 25. So what is this 25.33? That's not exactly what was observed. What does the hat mean again on y hat? Estimated or predicted. This is the predicted value. So very specifically, when I'm asked to interpret the y-intercept of the regression equation or the regression line, we would say that with 0 rubber bands, we would have a predicted value. Here, let me write this out here. 25.33 centimeters is the predicted what? Predicted value at 0, but what are we measuring? What is this? Yes, is the predicted distance or distance traveled when 0 rubber bands are used for the bungee cord. So some important things to point out here when we're interpreting the y-intercept in context, or we're interpreting the y-intercept of our regression equation. We always want to link this back to What is this regression equation talking to me about? So things I need to make sure to include. I need the actual y-intercept stated, right? I need to know what that is measuring, distance traveled. This is super important. You have to include that this is a prediction. The y-intercept of the regression equation, any values that we find from regression equations are predictions, and it's always very important in statistics to distinguish between, was this something that I actually collected and observed, or is this something that my model predicted? I actually have a funny comment about that in a moment. So 25.33 centimeters is the predicted distance traveled. I have to have this 0 in here, and rubber bands is our x variable. So it's 0, whatever my x variable is. Distance traveled is my y variable. So far, so good? Did you guys ever see or hear about the movie The Martian? It's a Matt Damon movie. What's the premise of the movie? He gets stuck on Mars. So this is one of my favorite books. I've read the book a disturbing number of times at this point. It's kind of like my comfort food when I go to read because I already know the story inside and out. There's a really funny scene in the book where the director, back on Earth, the director of JPL, is talking to the engineers, and he's like, why can't we communicate? Why is there no radio on Mars? I said, well, we never imagined a situation where this would come up. I mean, what are the chances? Based on all of their models, the chances were very, very low. In real life, they'd had 3 shuttle launches, and in one of those, they lost radio contact. So he said, well, it's 1 out of 3 based on our observed data. The model made a very, very different prediction. So it's very important to distinguish between those two. Observations can sometimes be very surprising. We can have outliers happen that our models are never going to account for. Last one on this side, number 6. What is the slope of the equation of the regression line? 7.46 centimeters. What does it mean? Yes. So remember, slope is the change in y over the change in x. So if this is positive, then I'm going to have a predicted increase. If it's negative, I'm going to see a predicted decrease. So I would say 7.46 centimeters is the predicted increase. Increase in what? Yes, distance traveled. How far? So it's the predicted increase in distance traveled for what? No matter how many rubber bands I add, it would increase only this much? With each rubber band. So 7.46 centimeters is the predicted increase in distance traveled for each additional rubber band. So things I need to make sure to have. Obviously, I need the actual slope here. You have to state that this is predicted. Increase or decrease, this is based on the sign of the slope. And one thing I want to point out, because I've seen this happen a couple times, and almost all of our examples in the notes we're seeing positive values. If you had a negative slope, I would not say negative 7.46 centimeters. I would say 7.46 centimeters is the predicted decrease. So I would let my words indicate the sign. I wouldn't put a negative because we can't travel a negative distance. And so I wouldn't have a negative with that there. So increase in the distance traveled, we have to address what y means here. This for each additional is super important. And then we have our x variable here. You could say for each or for each additional or per. Any of those key words that you guys learned probably back in Algebra 1 when you're reading story problems and trying to write equations. For each, for every, per, those would all be appropriate words to use here. So far, so good? All right. We are going to copy down kind of our important ideas that we went over with this. 3 big ideas. Making predictions. We want to be using the regression equation that is the a plus bx. Our graphing calculators have 2 forms of linear regression. We want to choose the one that is further down the list. It's usually about option 8 when we go there. So we want our y-intercept first, and then we want our slope. Be really, really careful making predictions based on extrapolation. For our residuals, residual equals a minus p, or RAP. That's another way you could remember that as well. When we talk about residuals, that's another place where if I found a negative from doing my subtraction, as I'm explaining what that means, I wouldn't put a negative value in here for my residual. I'd put the positive value, and then I would choose above or below to indicate whether it was positive or negative. When you guys get done copying this down, which I know nobody is yet, but when you get done copying this down, I want you to go and try the check your understanding to see how well you can replicate this on your own. See what you can do. I'm going to put my answers up for you guys to compare and contrast on this check. So interpreting the slope, with each additional mile run, the predicted number of calories burned increased by 160 calories. If your sentence isn't in the same order as mine, that's fine, but you need to have all of those important key features. Needs to say it's a predicted number of calories. Needs to say that it's increasing by 160 calories. You do need units with the slope. And you do need to have language in there that indicates it's each additional or every extra or a per or for each. And then you need to have your X in context there. For part B, when Michael does not run or when Michael runs 0 miles, the predicted number of calories burned is 20 calories. Remember, anything we get from our regression equation is a prediction. So when he does not run or when he runs 0 miles, because that's our X variable, predicted number of calories burned is 20 calories. For part C, we just plug 5 in. You should get 820 calories when you substitute 5 in for X. Bump it up on the screen a little bit there. For our residual, the residual was 90. The actual number of calories burned was 90 more than predicted for 5 miles. things that you need to make sure to include on an explanation of your residual. You're always doing actual minus predicted. Since we got a positive value, it was more, and you need to state what your X was here in context. So you wouldn't just say 90 calories more, have to have 90 calories more than predicted, and then you have to have that for 5 miles part. And then the very last one, I would not use this model for a marathon 26.2 miles. That is far outside of any of the data that Michael has collected. So that's an example of extrapolation. What he might be able to do running a 5K or a 10K or a half marathon doesn't necessarily compare to his continued performance as his body continues to exhaust here. Do you guys have any questions for me about the check? There's one last thing that I wanted to end with today. Kind of a visual understanding of what we're doing when we come up with these regression equations. Another name for a regression equation is the least squares regression line. So I want to look at a model here real quick. I don't want to take this off the screen if anybody still needs it, so snap a quick picture because I'm going to bring up a different website here. I do post all the notes on Canvas too, so if I ever go too fast and you're not able to snap a picture, you guys do have access to all of these. This last part is not in your packet at all. It's a visual understanding. You guys do have access to this as well. But here is an example of a data set. I've got this scatter plot. If I wanted to try to find the line of best fit for this, that regression line, I can move this around on my screen by moving these red dots. Where should I put this, generally speaking, if I was wanting to find the line of best fit? In the middle, okay. So what do you think? Is that probably the line of best fit? Do I need to move it at all? So what we want to do as we're finding, so this is kind of what's going on in the background with the calculator. If I show the residuals, the actual minus the predicted is coming from my line. If I show those residuals, is this minimizing the distance between all of those? So I would want to move this until I have this at the minimum distances possible to get my line of best fit. I want all of these to be as small as possible. I realize I can put it right on one, but that's going to make other places larger. So what I can do is show the sum of my residuals. So if I look at the sum of my residuals, it's at about 19.9. If I move that around, that value is going to change. But as I'm looking at the sum of my residuals, it's taking everything that's a positive and everything that's a negative and combining it. That's not always going to give me the least distance between these. If I, instead of looking at the sum of my residuals, I square those, now I've got this value down here. I can look at this from a visual perspective also and make these little squares. So I want these squares to be as small as possible. As I move this around, let's see what we can do. I want you guys to look at where it says the sum of the squares. Tell me what I can do to make it smaller. Like, did I get bigger or smaller as I moved it here? Bigger, so I'd want to take it back to where I was. It's getting smaller, but now it's getting bigger again. Okay, so I probably want to leave it more like here. If I move this one around, ooh, I got it down to 62 something. 61, 60. I'm getting pretty close. Do you guys want to see what the actual line of best fit is? And how closely we were able to match that? that blue line that just went on top of the red one. That is the least squares regression line. So that's what's going on in the background of your calculators. We don't need to calculate this by hand, but I thought it was a useful visual for what we're doing with that. Have a great rest of your day, guys. Homework 3.2 is due next Tuesday. So a little bit less than a week. Next Tuesday is when the next homework is due. Have a great one, guys.